To overcome the limitations, we have started a new topic, that is the probability model, and it says any model or any assignment satisfying two conditions. Number one, assignment for every sample point should be non-negative, and total assignment should be equal to 1. Such assignment is named as probability model. We have seen different examples based on the probability model. After that, we started another approach towards the probability, which is named as a modern approach called as axiomatic approach to probability. Under this approach, we made 3 statements which are true itself, labeled as axioms. Probability of any event always non-negative. Probability of whole sample space is 1. And if A and B are two disjoint events, then probability of A union B written as PA plus PB. On the basis of this, we have studied some theorems. First 3 theorems are trivial. You can prove with the help of axioms. I stopped my last lecture by giving the statement of total probability theorem. In that case, the statement was like this: probability of A union B equal PA plus PB minus P of intersection. Here we assume that event A and event B are not disjoint. They have some common element. And that is why this intersection part comes in the statement. This statement is labeled as total probability theorem. It is also known as addition theorem on probability. We will try to see mathematical proof of this statement and then we'll proceed ahead. Let capital A and capital B be two non-empty events of omega. We write event A union B by Venn diagram. It is a mathematician who suggested how to draw the diagrams for a set theory. We assume rectangle as complete sample space. In mathematics language, it is universal set. In statistics, we labeled it as a sample space omega. This is a circle which shows A, and this is another circle which shows B. I divide this A and B in 3 disjoint parts. 1, middle is 2, and third is part of B. If I want to indicate this by a set theory notations, 1 stand for element of A. This much, this is nothing but 1. So you can see it is not total A. It is part of A. So I write this one as A intersection B dash. Here dash means complement outside of B. Similarly, you can see this is a part of B but not a complete B, labeled as third part. How to write this by set notation? It is element of B common with outside A. So I write third part as A dash intersection B, first part as A common B dash. And middle is, everybody can understand, it is a common part between A and B. So now I want to develop probability of A union B. So by this Venn diagram, it is easily probability of 1 plus probability of 2 plus probability of 3 that can easily observe by using a Venn diagram. What is P1? P1 is probability A intersection B dash. I wrote here. What is 2? It is P of A intersection B. And what is third part? It is probability A dash common B. Now, probability of A intersection B dash written as P for A. That means if I take this entire circle, does it my answer of this? No. This extra coming in your circle, so that I subtract minus P of A common B. Middle part as it is plus P of A dash intersection B. That means I want this shaded part. So how I wrote it? I wrote completely B, probability of B minus this middle part because I don't want this. So this is the answer. This is the answer for probability of 3. This square bracket is probability of 1 and probability of 2 is directly A common B. This minus probability of A common B cancel with plus probability of A common B. So result you get P of A plus P of B minus P of intersection. This is the theorem for 2 events. We can generalize this theorem for 3 and more than 3 also. For example, I write theorem 5, total probability theorem for 3 events. Let A, B, and C be 3 non-empty events of omega. Therefore, probability of A union B union C will be PA plus PB plus PC, just like this statement. Minus intersection, minus A common B, minus A common C, minus B common C. But here, this part is coming extra. Here, probability of A common B common C is added. That is to be remembered. So this is the generalization of addition theorem of 2 events to 3 events. You can easily prove this by the similar guideline of 2 events. Draw the Venn diagram. Divide the Venn diagram in different disjoint parts and then write probability of union is probability of addition of disjoint parts. See how the Venn diagram look like. This is my entire sample space. Under this omega, I have 3 different events. I call this A, I call this as a B, and I call this as a C. Now I divide this total Venn diagram into different disjoint parts. 1, 2, 3, 4, 5, 6, and 7. So if I want probability of A union B union C, it will be addition of probabilities for these 7 disjoint events. And after that, follow the method of this type of notation and you will get right side of the proof. I can keep this as a homework for everybody and try to get it. If you not get, we can discuss it. Next theorem is Bool's inequality. If A and B are any two events of omega, then probability of A union B less than equal to PA plus PB. This theorem we can easily observe by using total probability theorem. P of A union B equal PA plus PB minus P of intersection. If I drop
करुण सर
this part,
सर आपकी आवाज नहीं आ रही.
if I drop this, if I drop this part, now you getting everybody?
Yes, sir.
Now if I drop this part, easily you can see PA plus PB become greater than P of union. For example, I say P of A union B is 0.8. So 0.8 equal 0.7 plus 0.2 minus 0.1. So 0.8 equal 0.7 plus 0.2 minus 0.1. Suppose minus 0.1 is dropped. So LHS become 0.9 and RHS become 0.9 and LH is 0.8. So by dropping this, easily you get Bool's inequality that is looking like this. But Boole suggested another way of proving the result that we can see. The theorem of Bool's inequality can be written for any events, can be generalized to any event. Probability union AI, it is union of two. Now it is union of n events less than equal to, this is a sign of summation, P of AI. That is nothing but plot of A1 union A2 union dash dash union AN less than equal to P of A1 plus P of A2 plus dot dot P of AN. So this is the generalization of Bool's inequality from two events to n events. We have next theorem. If A1 and A2 are two events of omega, probability of A1 intersection A2 greater than equal P of A1 plus P of A2 minus 1. This statement is for intersection of two events. You can make generalization of this. P of A1 intersection A2 intersection dash dash intersection AN greater than equal P of A1 plus P of A2 plus dash dash P of AN minus n minus 1. If it is for two event, it is 1, that is 2 minus 1. So if it is generalization for n events, this 1 will be replaced by n minus 1. So these statements you have to remember. Proofs are not much important, but this is important. Probability of union of two events called as total probability theorem or addition theorem on probability. We proceed to discuss some numerical examples. If A and B are two events of omega such that PA 0.6, PB 0.5, P of intersection 0.3. On the basis of this information, we have to compute these different type of probabilities. So if theorem is available, use it. If theorem is not available, try to solve by Venn diagram. Number 1, P for A dash. Easily we can write 1 minus PA, because PA plus PA dash equal to 1, it is theorem number 1. Also explaining remark of classical probability. So 1 minus 0.6, 0.4. P of B dash will be 1 minus PB. P of union, we have theorem. P of union equal to PA plus PB minus P of intersection. This is 0.6 plus 0.5, that is 1.1 minus 0.3, answer is 0.8. Probability of A dash intersection B, here we don't have theorem. So we take a help of Venn diagram. This is your Venn diagram. Treat this as a rectangle as omega. Draw two circles which are connected and locate your event. How to read this? It will be described as part of B common outside of A. So forget entire circle of A. Out of A but coming from B. So this line is my event. So I write this as P of B complete circle minus this unshaded part which is a common. So easily I get answer 0.5 minus 0.3, 0.2. This is reverse probability of A intersection B dash. Look the location. This is entire rectangle as a sample space. This is circle A. This is circle B. I want part of A common with out of B. So forget the circle B and take an element from A. If I want to write probability of this, I take complete circle of A, that is PA, minus this middle part which you don't want. PA given is 0.6, P of A intersection B given 0.3, result become 0.3. Next calculation is probability A dash intersection B dash out of A and out of B. I write this by using De Morgan's law. This is De Morgan's law. Probability A union B complete dash. And if there is only one dash, use a complement theorem. 1 minus probability itself. We have P of union in your hand before, that is 0.8. I use it here. So P of A union B is 0.8. So 1 minus 0.8 is 0.2. The last is probability of A dash union B dash. Again by De Morgan law, A intersection B complete dash is nothing but A dash union B dash. This is De Morgan's rule. When there is single dash for entire event, use complement. 1 minus 0.3, result is 0.7. You can solve this approach by other way. When there is a union, you apply addition theorem. So what is the other approach? P of A dash plus P of B dash minus P of A dash intersection B dash. We know P of A dash from previous calculation 0.4, P of B dash 0.5, P of A dash intersection B dash we got here 0.2. Put it there, get the answer. So this is a simple numerical example which you can solve either by using theorems. If theorems are not applicable, you can use Venn diagrams. So you have two ways to solve problems of probability in the notational form. Let us go ahead. Now I write descriptive problem which is parallel to this. See how it is parallel. The probability that a contractor will get a plumbing contract is 0.4, and the probability that he will not get an electric contract is 0.7. If the probability of getting at least one contract is 0.6, what is the probability that bit number 1, he will get both the contracts, bit number 2, he will get exactly one contract. Now you can see this problem is a descriptive. But what I say this is exactly same as question 1. How I can do that? I will transfer this information in the notational form. If you read the question carefully, it is for two information. Number 1, regarding plumbing contract. Number 2, regarding electric contract. That means question has information of two events. So I will start the solution by defining two events. A, contractor gets plumbing contract. B, contractor gets electric contract. Now I will write given information by notation. Chance of getting plumbing contract 0.4 given here. Chance of getting electric contract 0.7, that is PB. Sorry, not getting. So when it is not getting, I have to write a dash. So P for B dash 0.7. Therefore, PB become 0.3 by complement result. And what is the third information? Getting at least one contract. B, remember, when the word is at least, you have to use always union. So at least means either A or B or both, and that is written by union. So chance of getting at least one contract is 0.6. Now you can see easily this problem become parallel to question 1. Now I proceed to give answer. What is the bit 1? He will get both the contracts. That means person will get contract A and B. Both means A and B. So when you want to write and, use intersection. So probability of A intersection B. By using total probability theorem, P of A intersection B will be PA plus PB minus P of A union B. Because what is P of A union B? It is PA plus PB minus P of A intersection B. Change the side, you will get this statement. This everything is known to you. Just we derived by the notational form. Put it there, 0.4, 0.3, 0.6. So result is 0.1. Now second bit is probability of getting exactly one contract, not both, exactly one. That means either plumbing, if not electric, not both. So when I say exactly one, you can understand from this Venn diagram. This is complete possibilities. I have two events, that is two contracts. I want only A, that means this area. I want only B, that means this part. So this part will not come in your calculation. If you take this part, it comes A and B. This I don't want. So getting exactly one, that means addition of this plus this. This is written by notation A common B dash. This is written by notation A dash common B. Therefore, probability getting exactly one contract is probability A common B dash plus probability A dash common B. This will be written 1 PA minus P common B plus this is written as PB minus PA common B. Put the values, simplify. So 0.5 is a chance to get exactly one contract. This is 0.1 chance to get both contracts. So you can understand now, if such question comes, your step is to transfer this information in the notational form by looking how many informations are there. If information is for two things, define two events. If information is for three things, define three events, and so on.